Today we continue talking about Niels Bohr and his development of the atom and his model of the atom that we said was the orbital model of the atom. This should be repeat from last time, in that the electron with its lowest possible energy is known as the ground state. Because if you fall from the ground, it's going to hurt less. Okay? The lowest amount of energy would be transferred to you through falling. That's how I kind of think of it. When you are excited, you leap for joy. You make a quantum leap. Now, for some, it might just be literally getting off the ground. When you come back down off of that excited state, heat or light is given off. Now, some of these things I'm giving electrons humanistic qualities. They have no humanistic qualities whatsoever. We try to give them humanistic qualities so that we can try to develop some sort of a relationship and understanding of why they're doing it, what they're doing, their behaviors. Okay? They don't have humanistic qualities and or completely humanistic behaviors, but we try to give those analogies. So Bohr's model of the atom kind of gives us this. Now, Bohr used hydrogen as his beginning point. Why would he use hydrogen as his beginning point? Because hydrogen is the simplest of the elements. Hydrogen has one proton and one electron. If you're trying to find out where electrons are, it'd be probably a really good idea to start with the one that just has one. And so that's what Bohr does. Now, hydrogen in its natural state does not have any neutrons in it. It's just a proton and an electron. It is very, very simple. You don't get in the way with having neutrons present. A neutron that is present in hydrogen is known as deuterium. We'll talk about that later. If it has two neutrons, it's called tritium, and that's because of the atomic mass, and when we talk about atomic mass, we'll bring those up. Okay. Now, he was able to predict the hydrogen spectrum, the line spectrum, based on his information. However, it only worked for hydrogen. So now all of a sudden you're like, okay, this is great, this is awesome, but then now all of a sudden he starts, maybe he goes to helium. Probably not, because it might not have been known at the time. Goes to helium or goes to lithium, and it doesn't work. Then becomes the question, well, why did it work for hydrogen and it doesn't work for these other elements? That's because when those electrons find their excited state, they can go to any one of these higher end questions. Okay? Any of these higher level layers. Where they drop down can also be different. And therefore, it's going to change what line we see where. And when you have one electron moving and one electron maybe not moving, which one's moving, which one's not moving? I don't know. And then we start to find out that electrons are in different orbits in itself. When they start, they're in different orbits. They're not all in the first one. Actually, very few are. So they have to figure some things out. And that's where Bohr's model kind of like, roadblock. But it gives us a great start. And it is this great start that I think we can take a moment and kind of draw some of the Bohr models that might be helpful to understand what do we mean by these Bohr models and where they rotate to. You know, if we have the hydrogen model, I'm going to just put a little plus there. And then we have some orbits. I'm not going to draw really more than two because I only need one. So for a Bohr model, and if you look at your periodic table, cough, cough, hint, hint, nudge, nudge. When you look at your periodic table, cough, cough, hint, hint, nudge, nudge, you might find yourself looking, going, oh, one proton, one electron. Oh, look, the atomic number of hydrogen is also 1. I wonder if there's a connection. You would be correct. There is one electron. In its lowest possible state, it resides in that first ring. It's really nice. By the way, what row is hydrogen in? It's in the first row, right? It's on the top of the periodic table. It's in the first row. Well, okay. Let's look at another one. Let's look at another simple one, and let's look at, say, helium. What's helium? Well, helium has the atomic number of 2. So it's got 2 protons. I'm going to draw a couple orbits there. In a neutral, meaning no charge, the number of protons needs to equal the number of electrons because there's no charge. If you had more protons than electrons, you would have a positive charge. If you have more electrons than protons, you have a negative charge. But since they're going to be neutral, no charge. Which reminds me of a wonderful joke. Proton, electron, and a neutron walk into a restaurant, have a meal. At the end of the meal, waiter brings a bill to the electron and the proton. The neutron says, why? No bill for me? He goes, for you? No charge. The electrons, also in their lowest energy levels, are going to be in that first row. Because hydrogen's in the first row on the periodic table. Wasn't that just nice? It's kind of convenient almost. And so that's where it works. So, you know, I'm not drawing the neutrons in here because we know where they're located. We know they're with the protons. Their interaction matters something more in nuclear chemistry. We're not getting there yet. So let's predict one that gets a little crazy. Lithium. Lithium is number 3 on the periodic table. So it's got 3 protons. Because it has 3 protons in a neutral atom of lithium, we should have a total of 3 electrons. Now, where they go actually starts to become a thing. we need to fill the lowest energy first. And to fill the lowest energy first, we filled the 2 in the first ring. Now, we ask ourselves, well, what row is lithium in? It's in the second row. So that means we start filling up the second row when we get to lithium finally. We start to fill it up, meaning it takes a while to fill it up. Kind of near the end of that row, do we finally get it filled up. Now, I draw them out so that the electrons are kind of spaced out, very, very concrete, sequential. That's my nature. Okay? There are other methods. But that's just kind of, in a way, an introduction to what Bohr models look like. They'll get more complicated, and we'll get there when we need to get there. So, regardless of the problems that Bohr's theory had, it did give us at least a logical explanation of why we saw what we saw. And that's important. Sometimes saying the why and having 100% of this is why we see what we see is nice, but sometimes when you're dealing with so much unknown, a logical explanation is very important. It introduces the idea that electrons can have different energies, and it can be quantized. Meaning a number can be associated with it. Now, these energy levels we can look at as orbits in Bohr's model. In some way are still used in our current understanding of the atom. And what that is the principal quantum number. The principal quantum number, also known as n, is equal to the row number. The principal quantum number is equal to the row number. Now, if you thought there was a controversial topic, such as to be conservative or liberal, in physics, it became more of a issue of, are you a light as a wave person, or are you a light as a particle person? That was a very controversial topic in physics. Whether or not you believed light was one thing or another. Louis de Broglie comes out and says, you're both right. A mix of both is what's actually happening, and is actually how we should view it. And that light, when we talk about small packets of energy or singular light packets, photons, particles are the best way to explain what light is doing. When you start looking at multiple photons interacting together, they start interacting together in a form of a wave. And so now all of a sudden, light behaves as a wave. And it really comes down to how many light particles you're talking about. One singular light particle photon. That's all. Just one of them. But when you start adding the photons together, they start to make a wave. That we see as light waves. And so it's this wave-particle duality. Light is both a particle and a wave. It all depends upon how many you're really looking at. One singular photon is going to behave one way. But when you start getting more than one, you have that. And so that's when you have, and you can do those calculations with his theory, his numbers. The H is, again, Planck's constant. V is your frequency, wavelength. M is another value that we're not going to worry too much about. But it's the fact that wave can be both a particle and a wave at the same time. So neither is right. They're both right. They're both correct. It's now coming to figure out how do we blend those two ideas. Because like I said, it was very controversial to be one or the other. Oh, you're a wave light person. Oh, you're a particle person. You would, of course you would. But that's what you have with that. And that becomes, science can be just as separation as politics can be. But ultimately, we can figure out how to work together for that common purpose. Now, sometimes the science gets pretty crazy and difficult to explain. Then you have this other person come in and say, well, everything you think you know, you don't know. And that's Heisenberg and his uncertainty principle, or sometimes referred to as his uncertainty theory. Meaning the exact position and momentum, sometimes referred to as speed, because momentum is velocity times mass, of an electron cannot be known. The more you know about the position, the less you know about the momentum. The more you know about the momentum, or the more you know about the energy, the less you know about the position of the electron. To find the position of an electron, you need to try and slow the electron down to try and find out where it's at. In slowing the electron down, in theory, you're changing the amount of energy it has, because the speed is being changed. So to find out one thing, you're actually changing what's going on. And so you're like, okay, let's find the speed of the electron. Well, then you're not going to know where it's at. I like to think of this as early GPS. Or sometimes when your GPS just isn't quite working correctly. You're driving down the highway with your, well, I use Google, and I just drive down the highway with my Google Maps. And Google tells me when to take a left and when to take a right and how many feet and how many whatever miles till my next exit. And so I'm driving down the highway, and the next thing you know, it says, in a quarter mile, turn right onto exit 35. When you look back, and you're like, that was exit 35. Why is it off? That's because the early ones didn't get that position very good because your speed maybe changed or varied. You kind of needed to have a really good constant speed for that early GPS. Now it's much better. Okay? GPS satellites are working a lot better now. But that's why they kind of look at it is, all right, we're we can't stick a GPS locator on an electron. And we can do that to the murder hornets, but we can't do it to, an electron saying, okay, GPS tracker, where are they going? It doesn't work that way. It would be awesome, but it doesn't. And that's what Heisenberg says. To try and find something out, you're changing something else. When you change that other thing, you're actually changing the thing that you're trying to find. Now, when they said slowing down, it's really more of a trying to hit a photon at it. And they use a photon, shoot it at the atom, so to speak. How the photon comes off goes, okay, it hits something there, based on an angle in which they shoot it at and versus the angle that it comes off of. So there must have been, and here's the thing, there was an electron there. And it's never going to be there again because that photon knocked it off its course. It's now on a different path. The velocity has changed. And why we use velocity is because velocity is speed with direction. The direction of the electron has changed. The path in which the electron has changed. So now, therefore, now you don't know anything about that electron you thought you just found out something about. Because it's no longer there, and it's no longer going at that same velocity. That's essentially what Heisenberg's uncertainty theory does for us. Is it gives us this, what is going on kind of a thing. What is going on?